In this video, we're going to look at something called the reaction quotient. The reaction quotient will let us figure out two things. Number one, are we at equilibrium with the conditions given? Yes or no? And number two, if we're not at equilibrium, in what direction do we need to shift to produce a system at equilibrium? Now, sometimes you will not need to do this reaction quotient. If a system is at equilibrium, the forward and the reverse are happening simultaneously at the same rate. So there can't be any component that's at zero. Now, if I have this equation here, nitrogen, hydrogen, ammonia, if it's going forward and reverse, all three particles are present at equilibrium. So if one of those particles is missing, I know I need to shift in the direction that produces the missing particle. So we're going to first look for anything that might be zero. Zero. At equilibrium, we should not have any zeros. We'll shift in that direction to produce the missing particle. If you do not have any zeros, that's where we're going to calculate Q. The reaction quotient, it'll look just like K. It's going to be products raised to the second, the coefficient in the balanced equation, nitrogen to the first, H2, hydrogen to the third. The only difference is that when you calculate Q, you're using initial concentrations or partial pressures. We don't know if this is equilibrium. So we can't say that we're calculating K, because technically the equilibrium constant K is only calculated using equilibrium conditions. We don't know if we are at equilibrium by just looking at the initial conditions. So sometimes they'll have a little I in there, standing for initial conditions. So we calculate Q exactly the same way as K. And then we do this. We compare Q and K. And remember that these are both set up, Q or K. They're set up as a ratio of products over reactants. So if Q equals K, the system is at equilibrium. Excellent. We don't need to shift. However, what if Q is too big? If Q is larger than K, and I look at this ratio of products over reactants, I need to reduce the value of Q until we meet K. We want the system at equilibrium. How do I make Q smaller? Less products, more reactants. Less products, more reactants. We're shifting this thing in reverse. We're going to favor the reactants. What if Q is too small? If Q is less than K? Well, now I need more products. More products, less reactants. If I'm shifting toward the products, we're shifting in a forward direction. Oh, okay, so this Q is a good thing. It lets us compare Q to K and predict the direction of the shift if we're not already at equilibrium. Let's try a few. This is super easy. Okay, so we're given three sets of data, all for that same reaction, which I'll put that down again. It was N2 plus 3 hydrogen forming 2 ammonia, NH3. They tell us the equilibrium constant. There we go. 6 times 10 to the negative second. So let's call this like trial 1, trial 2, and trial 3. With these initial conditions, which sometimes they'll put a little 0, like we're at time 0, initial conditions, or sometimes they might write in a little I. Are we at equilibrium? And if not, in what direction will we shift? All right, so let's get after it. Let's do trial 1. I'll call this Q1. Products over reactants. Okay, so products, 1.0 times 10 to the negative third. That's my product. That's the ammonia. And we're going to square that. All over reactants. My nitrogen is 1.0 times 10 to the negative fifth. That's to the first. And my hydrogen is 2.0 times 10 to the negative third. And that's getting cubed. Okay, so we plug this in our calculator, which, I mean, these numbers aren't super crazy. If you wanted to take them out of scientific notation, you could. We're going to plug this in. If you're like a obsessive caret key person on your calculator, if you go like 1.0 times 10 caret negative 3, you might want to put these in parentheses so your calculator does order of operations correctly. But I'm going to get about 1.25 times 10 to the 7th, which is giant. Q is definitely larger than K. If Q is larger than K, obviously we're not at equilibrium. We need to reduce the value of Q. And again, we're always talking products over reactants. So I need less products, more reactants. This goes reverse. Reverse. That's all there is to it. It looks just like K, but we just don't know that these are equilibrium conditions. All right, let's do this again. Let's try Q2. I'll put this in as Q1. Here comes Q2. Q2. Products. My ammonia is 2.00 times 10 to the negative fourth squared over reactants 1.50 times 10 to the negative fifth, just to the first, which obviously you could leave that out if you want, and 3.54 times 10 to the negative first. And we're going to cube that. Alright, so we'll plug all this in our calculator. Divided by 3.54 times 10 to the negative first cubed. And I get approximately 0.0601, which is approximately the value of K. 6 times 10 to the negative second, yeah, it's about 0.06. Close enough. Let's say Q equals K. We are at equilibrium. No shift necessary. At equilibrium. Okay, you see how this works now? Okay, let's try the last one. Let's try trial 3. Trial 3. Q3. Products. 1.0 times 10 to the negative fourth squared. I always feel bad. Sometimes people will make that mistake when they'll get to the end and, oh, I just forgot that stupid exponent. I forgot that it's to the second power. So just be a little careful of the ratio in the balanced equation. Whoa, that's 5. 5 molar nitrogen to the first and 1.0 times 10 to the negative second. That's my hydrogen to the third. So plug all this in to my calculator, and I get about 0.002, which is too small. Q is less than K. If Q is less than K, we need to make Q bigger. How do we make Q a larger value? We need more products. More products, less reactants. We're going to shift this thing forward. We're going to shift it forward. Those are your only options. When you calculate Q, we're going to compare it to K. If they're equal, perfect. We're at equilibrium. Q is too big. We want more reactants, less products. We shift in reverse. Q is too small. We want less reactants, more products. We'll shift to make Q larger. Shift forward.
Now in the next couple videos, we'll look at by how much. So if I know I need to shift forward, by how much do I shift forward? Q will just let us know if we're at equilibrium, and if not, the direction of the shift.